And now we get to continue our discussion about IP networking, and this time by talking about IPv6, or at least an introduction to IPv6. Now, first off, when you start talking about IPv6, a lot of people, myself included, get a little antsy. Ooh, IPv6, those are really big, complicated numbers. There's letters in them. It's really hard. There's a whole different set of rules than what we learned about with IPv4. But once you get used to it, it does actually make life a whole lot simpler. And in fact, when you start comparing the amount of work you have to go through to properly subnet and segment out IPv4 and compare that to what you see with IPv6, IPv6 is just so much easier to work with. So with that being said, we're just going to talk about an introduction to it, go over a little bit of details about how IPv6 works and how we can make it easier to work with, and then later talk about more details for it. So IPv6 by the numbers. First off, let's talk about IPv4. When we talk about IPv4, there is a 32-bit number, which means we have approximately 4.7 billion IPs. Well, now, if you start thinking about how many IP-enabled devices, how many internet-enabled devices you may have in your home, you may have a laptop, a desktop, a phone, a tablet, a smart TV, a personal device such as Google Home or the Amazon Alexa. A lot of appliances are getting IP-enabled. You might have IP-enabled light switches. Everything is becoming IP enabled and able to communicate across the internet. So think about how many of those you have times the estimated world population, which is over 7 billion, and suddenly the 4.7 billion IPs is not enough to go around. So we then move up to IPv6 by the numbers, which is a 128-bit address, which gives us a total of 340 undecillion IP addresses. Supposedly that is more than enough for, I want to say, 10 addresses per grain of sand in the world. It's been estimated that we will be able to run IPv6 for 100 plus years before we run out of IP addresses. Great. That's awesome. We have tons of IP addresses. In fact, we have so many IP addresses that only 42 undecillion have been handed out across the entire globe, and not just not utilized, but handed out by the regional internet registries. Each region, so Americas, APAC, Asia, whatever the regional registries are, each of those regional registries then has 415 decillion addresses. And right now, if you separate all of those by the estimated population, that means that each person could have today 58 septillion IPs, unique IPs assigned to them. So we now have plenty of IPs, plenty of room to grow, but the numbers are scary. Yeah. Well, let's take a look at this by the numbers here in a slightly different realm. Basically, right here, this section in green of our pie is the portion that has been currently allocated out to the world. So right now you're seeing IP addresses, IPv6 addresses that start with 20 and 3F, or 202122 and so on all the way up to 3F. However, otherwise we have all these other ranges with plenty of growth to go. There are some unique address ranges such as the unique local, link local, multicast, and unspecified that are out there. However, this right here, the fact that only 1/8 of the entire possible range has been started to be handed out means there's plenty of room to grow. And in fact, not only is it only one small portion of it, out of the 001 range here, about 1% has been handed out to the regional networks, regional registries. ARIN for the US, LACNIC for Latin America, AFRINIC for Africa. I forget exactly how APNIC and RIPE NNC go in there. That's my own personal failing there. But so about 1% of that one section has been assigned out. So there's plenty of room to grow. You can get plenty of addresses today and not worry about where we're going tomorrow. We've just got it. If you need addresses, get addresses. So there are a couple of different address types. Briefly, there's a unicast, multicast, and anycast. One thing you may notice here that there is no broadcast. IPv4 uses broadcast addresses quite a bit. IPv6 does not. No broadcast addresses. The unicast addresses do have some specific types. There's the global unicast, which means internet addressable. There's a link local, which means it can only be accessed on the local network. And then lastly, loopback. This is compared to the 127.000 range that you see in IPv4. And there's just one loopback address as opposed to 65,000 possible loopback addresses as there was under IPv4. Well, let's look at some addresses here and let's simplify it since this is just an introduction. We don't want to go too far, but we do have some very difficult IP addresses here. For instance, here in the preferred format, we see that's a really big number. Somebody asked me to say that. I would not be able to. At least definitely not from memory. So there's a couple of rules we can use in order to optimize the writing of these IP addresses. The very first one is to omit the leading zeros. So after this colon right here, for instance, there are 2 zeros. Now, with IPv6, there's some rules, and basically, hey, between these 2 colons, I should have 4 items. And if some of those are zeros, if they're left off, what I can do is I can go ahead and just fill them in. I know I'm supposed to have 4. If you only give me 2, then I know that I need to fill in 2 zeros. Now I have to put some rules here and specifically say they have to be leading zeros, because I don't necessarily know if the zeros here are here in the front or in the middle. So I have to say I can allow you to take the leading zeros out after the colons and simply rewrite it without those, which is basically what was done right here. The 2 zeros after the colon were removed, and the computer can just automatically figure out I'm supposed to have 4 items in there. I'm only seeing 2, so I'll just insert 2 zeros in front of that letter F. Same thing here. Well, we had 4 zeros. In theory, they're all leading zeros, but I still have to have at least 1. So I put 1 0, and then I know all the other everything else in front of that is 0. Same thing here, all zeros. 00 AA. I can remove these first 2 leading and then just write AA, and same with 271, 271. So if we look at this first example, well, FC80, there's no leading zeros there, so that's FC80. I then have a series of zeros. I have to have at least 1 number between the colons, for this rule anyways. So I write 1 0 and then my colon. Same thing, 4 zeros. Well, essentially I have 3 leading zeros, so I can drop out the first 3 leading zeros and then do my 0, colon. ACAD, no leading zeros there, so ACAD. And then leading zeros, leading zeros, leading zeros, and leading zeros, which means I can simplify this. And the number 1. Right. So there we go. There's a simplified number. This number is a whole lot easier for me to be able to read and write and possibly even remember than the prior one. Well, let's try that again for the second one. FE80, again, no leading zeros. ACAD, no leading zeros. Here I have 3 leading zeros, so I'll just do the 1 0. 1 0, so 197. Leading zeros, leading zeros, leading zeros, and then no leading zeros. So 0, 0, 0, and FF 01. Great. So I can remove the leading zeros. That makes it a little bit easier to read. It's still kind of a pain. Well, that's rule number 1. If there's a rule number 1, there's probably a rule number 2. Rule number 2 is that we can omit the all 0 hex tets. One thing to note is you can only do this once. So just like with rule number 1, it had to be the leading zeros, so we knew exactly where to fill them in. We have to have only one time that we're removing the all 0 hex tets. So what that means is we look through here, each one of these sections is referred to as a hex tet. Basically, for hexadecimal numbers, it's a hex tet. So there are 1, 2, 3, 4, 5, 6, 7, 8 hex tets total. Here we can see that we have a group of all zeros right here. So I can omit the all 0 hex tets and just simply replace it with a double colon. Now I can only do this once, but I simply take the largest chunk, the largest series of all 0 hex tets, and I replace them with a double colon. So if we look at the example here, well, we have all 0 hex tets, and we have all 0 hex tets. I look at these, I know I can only do this once. I can only omit them once. I look at the 2 of them. Well, here I have 2 hex tets, and over here I have 3 hex tets, so I probably want to do the largest of them. So I'm going to stay with the 3. So in that case, FC80, 0000, 0000, ACAD, colon, and now I omit all those zeros, 0001. Well, that makes life a whole lot easier. Do the same thing here. I have all zeros, and I have all zeros. Here I have 1 of them. Here I have 3. I'm going to want to omit the largest one because it's the easiest one for me to write. So, the same thing. FE80, ACAD, 0000, 0197, colon, FF01. Now, I could have gone the other way. For instance, if we look at this second example here, or I guess the first example here, I could have omitted the first set of leading zeros, of all zeros. So in that case, FC80, colon, oops, ACAD, 0000, 0000, 0000, 0001. Both of those answers are technically correct, and the computer is smart enough to see this double colon here needs something to fill in, and so it's going to look at the rest of the address and say, I'm supposed to have 128 bits, I'm seeing less than that, so I'm in this double colon, I'll just fill in with all the zeros possible. Either one is technically correct. The first one, where we omitted the 3 hex tets, was probably the easiest one for us to write and easiest one for me to say. So the first option there would probably be the most correct, even though both are technically correct. All right, and then lastly, well, we can combine rules number 1 and rules number 2. So here we have our preferred format, the full 128-bit address with 8 hex tets. We then look at the leading zeros. And we simplify it right there. We then look at the all zero hex tets, which are right here, and we replace it with a double colon, and there we have simplified our address as much as possible. So let's try that for our examples. FC80, we're just removing the leading zeros. 00 ACAD 0001, and then we look at the all zero hex tets. Again, we have 2 options here. We have right here we have 2 all zero hex tets. Right here we have 3 all zero hex tets. I'm going to want to simplify this as much as possible, so I'm going to go with the largest of them, which then gives me FC8000 ACAD : 1. Well, now I'm making the addresses much easier for me to understand. Let's try one more with an FE80. So again, all leading zeros, FE80 ACAD 0197 000 FF01. And then we look at the all zero hex tets. Right here I have 1. Over here I have 3. I want to simplify as much as possible to remove the 3 consecutive zeros. So FE80 ACAD 0197 : FF01. And that's it. That's the way that we can take the more complex IPv6 addresses and begin to simplify them into something that's much easier for us to read and write. And if we need to reconvert it or reinflate it back into the larger address, it's a piece of cake for us to do by simply replacing the all zero hex tets until we have the 8 hex tets total, and then inflating with the missing leading zeros in order to get 4 hexadecimal numbers in each of the hex tets.